In this goal, we are going to be talking about kinetic energy. Kinetic energy is energy of motion, and it's a trade-off between potential energy and kinetic energy. And the classic example is this roller coaster right here. So when I'm climbing with my car up to the top, I am increasing the potential energy. In this example, the potential energy is a gravitational position. So the higher you go, then the more potential energy you have. In chemistry, the potential energy is found in the bonds. So if I have a certain number of bonds, that potential energy is stored in those bonds. So as soon as those bonds are broken, the potential chemical energy is transferred to a kinetic energy. So the molecules will move faster because maybe heat is released. Let's go back to our roller coaster example. So we have our car traveling up to the top. At the top, we have a maximum potential energy. As it slides down, that energy is changed to kinetic energy. And then I have a loop. So I will have an increase in potential energy as it goes up the loop. And then I will have a release of the kinetic energy as it comes around. And so the same thing happens in chemistry. We have a potential chemical energy stored in the bonds. And then when they are broken, then that potential chemical energy is transferred to kinetic energy. Kinetic energy is defined as 1/2 times the mass times the velocity squared. So M stands for mass. And in chemistry, where do we figure out what the mass is for our molecules? That's right, it's the periodic table. V is for velocity, or how fast our particles are moving. So these can be atoms, these can be molecules. You will not ever solve for this equation, but you have to know the relationship between kinetic energy and mass, between kinetic energy and velocity, or between mass and velocity. So in class, I passed out a popsicle stick. And in that popsicle stick, I had students write kinetic energy slash T for temperature on one side, M for mass on one side, and velocity on the other side. So we're going to use this little manipulative to help us understand the relationship. So looking at the equation, because mass and velocity are on the same side, they are in an inverse relationship. So what this means is if my mass increases, my velocity will decrease. And we can use our little popsicle stick to help us. So one thing will always stay the same. And if my mass and my velocity are changing, then the one thing that's staying the same is the kinetic energy. So with your thumb or your finger, you're going to put that over the middle, showing that that property stays the same. And then if you increase the mass, so you will tip the mass symbol up like a seesaw. And so that means as the mass increases, you see that the V will go down, showing that the larger molecules will travel slower if you're at the same temperature or at the same kinetic energy. And you could do the opposite. So again, put your finger on the middle. This time you're going to tip the mass down. And so your smaller masses, you will see, will have a faster velocity. So they'll be traveling faster. We can also do the same thing with looking at the relationship between kinetic energy and mass or kinetic energy and velocity. So this is a direct relationship between kinetic energy and mass and between kinetic energy and velocity. So using your popsicle stick, this time let's keep the mass the same. So if I'm looking at the same molecule and looking at two different situations, so I'm going to put my finger over the M. If my kinetic energy or my temperature increases, what will this do to the velocity? And that's right, you'll see it go up. So if your kinetic energy goes up, your velocity will go up. Let's look at a different situation, this time with keeping our velocity the same. So if I have two molecules going at the same speed, I will put my finger over that velocity on the the popsicle stick. Then I can manipulate my popsicle stick like a seesaw or like a lever. So you will see that if the mass increases, what does that do to my kinetic energy if I have two molecules traveling at the same speed? So you will see that as the mass increases, your kinetic energy will also increase. And you could do the same thing with a smaller mass. This time that we see that if you have a smaller mass, then your kinetic energy will be smaller. So looking at the trend, we see that if we have, looking at kinetic energy is the same, then as the mass goes up, the velocity goes down. So an inverse relationship, and vice versa. As the mass goes down, the velocity will go up. And then if we look at keeping the velocity the same, we see that as the heavier mass we have, then the more kinetic energy it will have, and vice versa. So the smaller masses will have smaller kinetic energy if they're traveling at the same speed. And then we can look, if we're looking at the same molecule, as our molecule moves faster, the kinetic energy goes up. As our molecule moves slower, the kinetic energy goes down. So you can use this little manipulative. Hopefully you understood it. And you need to know the relationship. So inverse between mass and velocity, and then a direct relationship between kinetic energy and mass, and between kinetic energy and velocity. This is the first example that I gave you, showing that the equation, you can rearrange it and have situation one with your first molecule, and here's my second molecule. And if the temperature is the same, then my kinetic energy is the same. The average kinetic energy is measured through temperature. So that's why I have the T and the KE in the middle together, because that's how you measure kinetic energy, is with the temperature. So if your temperature is the same, and I have situation one, and I have situation two, and I have two different size molecules, I can see that their kinetic energies will be the same, and then I can rearrange the equations to solve this equation at the bottom. Again, I'm never going to really solve it, but I can look at the relationship. If I have a very large mass compared to a very small mass, how do we get this equation to equal each other? And it's through looking at the velocities. So a large mass will have a very small velocity. A small mass will have a very large velocity. That's how we can get these two equations to equal each other. So again, an inverse relationship. So at the same temperature, your smaller molecules are going to be moving faster. Your larger molecules are going to be moving slower. Another way to look at this principle is to look at what's called a Maxwell-Boltzmann distribution curve. And in this curve, I have three different gases. They are all at the same temperature. We briefly mentioned the Kelvin temperature scale at the beginning of the year, and we can see here that they're all at the same temperature because they're all at 300 Kelvin. Well, looking at the periodic table, I can figure out the masses for chlorine, for nitrogen, and for helium. And we can look at the distribution curve. In a distribution curve, you see that not all molecules are traveling at the same speed. For helium, I have some that are traveling really slow, and I have some that are traveling really fast. But we can see helium, compared to the other two gases, has more molecules traveling faster. And that is because it's such a small molecule. So again, the smaller mass will have a very larger velocity at the same temperature or at the same kinetic energy. Let's look at the other two molecules. Let's look at the chlorine. So looking at the chlorine, it also doesn't have every molecule traveling at the same speed. I have some that are traveling slower and some that are traveling faster. But you can see overall, compared to the helium, more are traveling slower. So overall, they're traveling slower than helium is. So the average speed is a lot slower than helium. And then we see that nitrogen is just right there in the middle. Again, has some molecules traveling slower, some traveling faster, but overall the average speed is right in the middle between the chlorine and the helium. Here's another distribution curve, this time looking at the same molecule. So this is all nitrogen, but now I'm looking at different temperatures. So what happens as the temperature goes up to a molecule? Well, it travels faster, and we can see this. So we have a same sample of gas at these three temperatures, and so you can see as the molecules start speeding up, that the curve kind of flattens out, and we end up having more molecules traveling faster in comparison to the other ones. So again, you still have some renegades that are traveling slow, but overall, we have more molecules traveling faster at a faster temperature. And remember, we use temperature to measure kinetic energy. So as my temperature goes up, my kinetic energy goes up, and my molecules will move faster. It's a direct relationship. Let's do an example problem applying our knowledge that we learned with these relationships. So I have two questions here. Which of the following particles will have the higher velocity at the same temperature? So the temperature is the same. If you want to use your little popsicle stick, that means you're going to be putting your finger right here in the middle. Again, mass on one side, velocity on the other. So we need to know the mass of our two particles. Looking on the periodic table, I can look them up. So hydrogen is 1 gram per mole, and I have two of them for a total of 2 grams per mole. And let's look at oxygen. I have two of them, and there's 16 is the mass. So for overall mass of 32 grams per mole. All right, so which of the following particles will have a higher velocity at the same temperature? So if I put my finger right here and if I tip my mass down, I see that if the M goes down, the V will go up. So it's just like a seesaw. So I see that hydrogen will have the faster velocity at the same temperature between these two molecules. Go ahead and stop the video and do the second example and make sure you understand how to do problems such as these. Okay, we're back. So helium has a mass of 4 grams per mole, and carbon is 12, and each hydrogen is 1, for a total of 16. So 16 versus 4, I find that helium is the one that's going to be moving faster because it's the smaller molecule. Here are 3 more examples. Go ahead and stop the video and work through these problems, and then I'll come back with the answers. Okay, and question number 1, we have helium and carbon dioxide. So looking up their masses, we find that helium has a mass of 4 grams per mole and carbon dioxide is 44. So 1 carbon and 2 oxygens equals 44. So both are traveling at the same velocity, so going at the same speed, which has the largest kinetic energy. So to kind of picture what's going on here, if you had a golf ball and a bowling ball moving towards your shin at the same speed, which one is going to hurt more? And you might say, well, the golf ball will hurt, but the bowling ball will probably break my leg. So that is because of all the mass behind that bowling ball. So the one that has the largest kinetic energy will be the larger mass. And so that would be the CO2 with the 44 grams per mole. Question number 2. So we have oxygen at different temperatures. What happens to the kinetic energy of the oxygen if the temperature drops from 32 degrees Celsius to 0? So we have a slowing down of our temperature. So we'll have a slowing down of our kinetic energy, and that is the answer. Okay. So as the temperature drops, the kinetic energy drops because remember, temperature is measured, or kinetic energy is measured through temperature. So my kinetic energy will drop. So the molecules will be moving slower. The mass stays the same because we're just looking at oxygen. So that might be another question I could have asked is what happens to the speed as the temperature goes down? Because my kinetic energy goes down, then my velocity would also go down. Let's look at question number 3. Question number 3 is kind of a trick question. Let's see if you discovered the trick here. So we're comparing two molecules, both at the same temperature, which has the highest kinetic energy. And remember, kinetic energy is measured through temperature. So the answer is they have the same kinetic energy because they're at the same temperature. So I didn't even have to look up their masses. So same temperature, same kinetic energy.